We're on page 27, topic 7, and we're going to do examples of applications of a straight line with two problems on this page, problem 8 and problem 9. So we're going to do these two problems. Let's get started with problem 8. So here, what are we told? The population Y of Montreal in millions has been growing linearly in years since 1960 X as follows. So here we have the equation, and as we said, Y is the population and X is years. So population, years. What was the population in 1960? So that's the first problem. What was the population in 2000? When will the population reach 4 million? So let's go through these three parts. First of all, we have to realize that this formula was started in 1960. So in 1960, X was 0. So we set X equal to 0 in the formula. Y equals 03X, 0 here for the X. 0 times 0.03 is 0. And so Y is 1.8 because the Y number is in millions. That's what it says here. So the population in 1960 was 1.8 million. B, what was the population in 2000? Well, if the formula started in 1960 or was originated in 1960, we're in the year 2000, let's say, that 1960 to 2000 is 40 years difference, so X is 40. Because the population depends on the number of years since 1960. We're talking about the year 2000. Difference between 1960 and 2000 is 40, so we put 40 in here. We multiply 40 by 0.03, and we get 1.2. Now, what we're saying is that each year since 1960, the population is growing by 0.03 million. Okay, that's what we're saying. So, third part of the question, when will the population reach 4 million? So you want the Y to be 4 here, and then you're going to compute the X. In A and B, you were given the X values. In one case it was 0 and 4 and 40. Now you're given 4 and asked to calculate X. So 4 equals 0.03X plus 1.8. Now you bring the 1.8 over to this side, and it becomes minus 1.8. 4 minus 1.8 becomes 2.2. Here you have the 0.03X. You divide the X, 0.03X by 0.03 to get 1X. And you divide 2.2 by 03 and you get 73.3 years. So when you add the 73.3 years to 1960, you get 2033.3. So in the year 2033.3, the population will reach 4 million. This is a simple application. So again, let's go over this again. Y is our population, 0.03 times the number of years from the base year 1960. The first two problems, one was in 1960, X was 0. And the second part was 2000. That was 40 years later, so we put 40 in here and calculated Y. And the third part says, when will the population reach 4 million? So Y is population, so you put 4 here. Now, this is in millions, so you don't put the number 4 with 6 zeros in because this is already in millions. So let's go to the next problem, which is problem number 9. And here we're told that when you print posters, it costs $85 to print 100 posters and $125 to print posters, 200 posters. So we want to express the cost Y, that's how much it's going to cost to print printers, in a linear equation with, depending on the number of posters printed. So how does the cost Y depend on the number of posters printed? That's what we're asking. Now, here's our Y. Cost is our Y. M, X is our number of posters printed, and B is the Y intercept. So Y is the cost and X is the number of posters printed. In the equation, Y equals MX plus B, because we're asked the cost Y in terms of X. So we put the Y here, MX plus B. How are we going to What information are we given? We're given 2 ordered pairs where Y is 85 and X is 100, because X is the number of posters. So 100, 85, and then 200, 125. So this represents X1, Y1, 185, X2, Y2, 200, 125. So since we know 2 ordered pairs, we know that the slope is the change in Y over the change in X, Y2 minus Y1 over X2 minus X1. We take the difference in the Y's, 125 minus 85, that's here, over 200 minus 100, 200 minus 100. So we get 40 over 100, which is 0.4. So we now know that Y equals 0.4x plus B, but we don't know B. But what we can do is take the ordered pair 200, 125 into the equation. Let's say take this one here, or we can do this one. It doesn't really make any difference. We'll get the same answer, but we'll put 200, we'll put, 125 for the Y and 200 for the X right here. Y is 125. When X is 200, we compute this plus B. Now, 0.4 times 200 gives us 80. So B, we transpose the 80 from the right to the left, subtract it from the 125, and we get 45. Therefore, Y equals 0.4x plus 45. We can check this equation with the other ordered pair, 85, 100. In other words, we use the first ordered pair to get B, but we can check the equation with the other one. And we're going to substitute 100 posters into the equation to find Y. So Y equals 0.4 times 100 posters, plus 45, we get 85. And that's what we should get because one of the ordered pairs is 185, 100, 85. So we know when X is 100, Y comes out to be 85. This equation, by the way, tells us that the setup or cost to fixed cost to print the posters is $45. no matter how many posters are being printed. Imagine you walk into a print shop and you want posters printed. What the printer tells you is that, look, he needs to set up the machine. He needs to put in the ink and do various things, no matter how many posters you're going to be printing. So that's your fixed cost. That's the B in this equation, $45. So now let's take a look at B. Now that you have the linear equations, how much would it cost to print 500 posters? So we go back, we've derived the equation. We derived it as y equals 0.4x plus 45. And now we want to know how much it costs to print 500. So x is the number of posters printed. 0.4 times 500 is 200. 200 plus 45 is 245. So here we have the fixed cost. Here we have the variable cost, which will depend on the numbers of posters printed. So you have a 45 base cost, no matter how many you want. And then, in a sense, what you're saying is that for each poster that you want printed, it's $45. So you, in a sense, could do this in your head and say, well, I've got 500 posters to print, so 500 times 40 cents gives me 200, and then I need $45 as my fixed cost, or just to set up the machine, so I get a total of 245. So you could figure it out in your head from the information that you're given, or you could compute the number from this equation here. Now, just to finish up here, we could, if we have 2 points, we can derive a single formula that gives the equation of a straight line connecting these points. In other words, what we've done here is usually to calculate M and then use one of the ordered pairs to calculate B. But we could set up one formula. What do I mean? Here's the formula that we want to set up right here. So we call that 1. Now, what we could do is realize that M is the difference in Y's over the difference in X. So now we could substitute for M with this formula. So that's one thing we can do. Now B, this B value is equal to Y minus MX. If Y equals MX, then B must equal, if I transpose this over to the other side, Y minus MX. And if I put an ordered pair for the X's, they must go together, X1, Y1. Then I have a value for B. And now if I again substitute for M here, this over here, I get Y1 minus M. I'm substituting this, because I got it up here, and I get that. So now what I do, I've got equation 1. I've got equation 1, which I'm working with. I've got an equation for M, and I've got an equation for B that I can substitute into Y equals MX plus B. So here we have Y equals MX plus B, and B was Y1, this part of the formula right here. So this is this part of the formula right here. So you see, if I substitute 2 and 3 into 1, I come out with this formula. Let me go over this again. We have Y equals MX plus B. We have a value for Y, which is the difference in the Y's over the difference in the X. And we're only going to get a formula, trying to get a formula that will, in one step, will give us the equation of the line just using these. So we just do the whole thing in one calculation. And now, if I substitute for M here, I get this, put this into the M. I realize that b is equal to y minus mx, and I substitute the ordered pair here. I could put y2 and x2 here. That's perfectly acceptable. Will give me the same answer. Now for the m in this part of the formula here, the y1 is this y1, this x1 is this x1 here, and m is that value here, so I put it down here. Now we go back and we substitute this into this, and for b, which is right here, we substitute this whole thing and we get that equation right here. So here we now have one equation that will give us the equation of a straight line. So let's take an example. Let's say we have an example 1, 3 and 5, 11 as our two ordered pairs. I put this into these formulas here and I get the difference in the y's, 11 minus 3 over 11 minus 3 over the difference of the x's, 5 minus 1. This x is this x. I'm substituting into this formula. This part here, right here, is the same as that part over there. So I'm going to substitute 11 minus 3, 5 minus 1 for that. x1 is 1. X is my variable, and y1 is 3, so I put that right over here. And this works out to be 2. This whole thing works out to be 2, so I get 2x plus 3. This is minus 2 times 1 minus 2, y equals 2x plus 1. So just using this formula and two ordered pairs, I can come out with that formula. Now, I'm not suggesting that you memorize this or anything like that, but it's interesting to see how you can manipulate the formulas to give you a, albeit complicated, but an answer that works. Normally what we do here is we calculate the slope and then we calculate b. And this is just one formula. Now, as I said before, right over here where I wrote y minus mx1, I could have written y2 minus mx2, and we'll get the same answer. I mean, the formula would be slightly different, but I would still get this answer right here.